It's my pleasure to introduce our next speaker, Dr. Kenneth Carpenter. He's a longtime colleague and friend of ours. Now, we worked on a Hubble Space Telescope instrument team together back when I was in graduate school, and Ken is currently still working on Hubble Space Telescope as the operations project scientist. He's also taken on a new task as the ground systems project scientist for the upcoming Nancy Grace Roman Space Telescope, which he may mention in his talk. Today, he's going to give us the latest on the Hubble Space Telescope and how he and others worked to help it recover from a computer problem during the summer. His talk is called Bringing an Icon Back to Life, Recovery of Hubble Science Operations from Payload Safing in June 2021.
Good day, everybody. Thank you for inviting me to come back, even if it's virtual, to Fort Collins Comic-Con to tell you one of the more exciting Hubble stories of the year. As many of you probably know, we had what's called a safing of the payload on the observatory back in June, which took Hubble out of science operations for about a month, which is a very long time for us to do that. And it was a very challenging situation that required the best of our engineering team to recover from and get us back to science operations. So spoiler alert, we did successfully recover in July of 2021, and we were back to normal science operations now. What I'm going to do here is tell you the story of what happened, why it took so long to get back, and where we stand today. So put on your seatbelt and hang on, and let's go through the story of bringing an icon back to life, the recovery of Hubble science operations from the payload safing in June 2021. Okay, to paraphrase the opening title song from one of our favorite shows, it was a long road getting from there to here. These first two pages here, I'm just going to give you the overview of what was going on. I'll go into the details later, but in June 16th, these are basically highlights, headlines from NASA press releases that came out. So on the 16th, NASA put out a release saying that we're working to resolve an issue with the payload computer, basically going public with the fact that we had an issue with the payload computer on Hubble. And basically we're not taking science operations. The telescope itself was okay, it was healthy, and we had power and thermal control over it, but none of the science instruments were working, so we couldn't take data. June 18th acknowledged we're continuing to work on restoring it. On the 22nd of June, we began testing to try to pin down exactly what the issue was. We were having trouble doing that, and try to figure out how to restore computer operations. Did some more testing on the completed testing by the 25th. And by the 30th, we were preparing procedures to try to turn on some additional backup hardware to get back to normal operations. We had tried flipping some individual components before that, but this preparation starting on the 30th was to do a major reconfiguration of the hardware. By July 2nd, we had completed the preparations to test the procedures on the ground. Then we went into a multi-day series of tests, which we finished on July 8th. Then we went into a review on July 12th to assess and minimize the risks of doing this switch to the backup side of the telescope. That was completed on the 13th. In parallel with all of that, we were working to continue to identify the cause of the problem and sort of hope we would get there, would understand that before giving the go, no go for the side switch, making sure we were actually doing the right thing. So we did identify what we thought the problem was there, began the switch on the 15th, and by the 16th, we could say we were successfully switched and returned, took our first observations on July 17th, which were released. Well, actually, operations began on 17th, and the first images came out on the 19th. So that's the 30,000 foot overview of what was going on. So let's see what was actually involved in here. So Hubble entered this safe mode, which it does when something on board happens that it doesn't fully understand and is outside normal operating parameters. Basically, is to protect itself, to make sure anything worse happens to the telescope because it's operating abnormally. That happened on Sunday, June 13th. All our phones, pagers, emails went off at the same time, which is always a bad sign, telling us that something called the NISC-1, the NASA Standard Spacecraft Computer, version 1, which is the computer that controls the payload. And by that, we mean basically the science instruments, which is the rest of the observatory is designed to support and enable. So we have a payload computer. We also have a spacecraft computer that runs everything else. And that is, we call that the HST 486, which is because it's based on an Intel 486 chip, which sounds, really, really ancient compared to what we have on the ground today. But that's actually the enhanced computer that was sent up in one of the early servicing missions, and provides more than enough capability for running the spacecraft. A lot more memory than the original computer, and plenty of processing power. And importantly, it's radiation hardened, so it can operate in space, which is why the latest generation of computers are not automatically put on board, because it takes a while to validate them and make sure they will operate in the hot cold cycling and the vacuum of space. Anyways, the payload computer and the spacecraft computer are supposed to talk to each other. There's supposed to be a keep alive signal that comes from the payload computer going to the spacecraft computer, and that stopped. So at that point, a device called the SSCDH, the Science Instrument Command and Data Handler, dropped into fixed format. And you don't need to know exactly what that is, except that in that format, we get very limited telemetry on the instrument packages. And therefore, it makes it much harder to see what's going on. When it's in normal operating format, we get a lot of telemetry and we can see a lot more info and more quickly figure out what's going on. So a procedure called SMAC20 executed that safed the payload, basically turned off the instruments except for their survival heaters and the like, and made sure that nothing further would happen to them, since we lost this visibility that the SSCDH provides to us. We did get 2 good hardware dumps off of payload computer after this happened. And the spacecraft computer, the 486, and the rest of the spacecraft remained fully functional. So we were actually, the telescope was actually slewing from target to target in the pre-planned science plan. It's just when we got to the targets, we couldn't observe anything. But it was safe and we were at power positive attitude, so we just let that continue for a while. Pretty quickly, we realized the problem did lie within the Science Instrument Command and Data Handler, and inside that is where the NISC-1 payload computer is located. So at this point, we didn't know if it was the NISC that was a problem or something else in the SSCDH. Okay, so just to orient folks, hopefully you can see the cursor on my screen here. Where is the SSCDH? On the left side here, you see a view from the outside of the telescope. Aperture, open aperture door at the top right, going down the sunshade tube here. We have a ring of instrumentation behind that for science instruments. The mirror is actually up in the center of this ring, and there's support module down here with all of the other support instrumentation. The SSCDH is in one of these bays on the side of this donut, which if you look from the bottom up is bay 10, between some reaction wheels and the data management computer down below. So basically off here on the side. Okay, I thought a brief primer on the SSCDH is useful here, since that's basically what we're talking about. This device keeps all of the science instrument systems synchronized. It processes, formats, and temporarily stores on the data recorders on board Hubble, and then transmits to the ground all the science and engineering data. So it's basically a huge routing system for the commands going into the instruments and the science and engineering data coming out. Data enters the SSCDH of something called the Control Unit Science Data Formatter, CUSDF, and receives ground commands, data requests, science and engineering data, and system signals, formats and sends all of the commands and data to designated destinations, and controls and formats data versus via a microprocessor. So it's a busy little device sitting in the exterior part of that donut. Oops, let's go back here. Data then flows out of that through what's called the standard interface, or STINT. And that's the communications bridge between the central processing module and the CUSDF. So all of these things are going to come up in the conversation. I apologize for all the acronyms here, but it's NASA, and that's part of the job, as it were. Okay, inside the SSCDH, we have the NISC that we talked about before. That contains a central processing module. It runs the software executive, moves data, commands, and operates applications, and stores software and instrument commands in one of 4 memory modules. We use 1 memory module at a time, so we have 3 backups for situations where something fails. They're 64K each, CMOS memory units, so pretty small. It's not a lot of room here, so you have to be very efficient in your use of these memory modules. There's a remote interface unit, RIU, that transmits commands, clock signals, system signals, and engineering data between the science instruments in the SSCDH. So that's an in-between a router. Again, there's a lot of routing type devices in here to keep track of and move all of the data. Power control unit does the same thing for power as opposed to data, distributes and switches power and clock among the different components. The SSCDH orbital replacement unit, ORU tray, is what all of this is mounted on. So it's just sort of like the inside of a door, basically, that has the SSCDH component. And that was replaced along with all the components in 2009 because we had a failure on side A of the original unit. So we cobbled together, we delayed the last servicing mission, cobbled together a replacement unit from leftover parts in the ground because we didn't have a replacement unit pre-built, and then launched it and replaced the SSCDH in May of 2009, and began operating that new unit on side B because the spacecraft had been switched to that because of the previous failure. So the old unit was operated on side A of the electronics. The new unit has been operated on side B ever since it was installed in 2009. And the way we are currently set up, science operations are not possible without this tray functioning. So that's where we sat after the failure with a non-functioning science instrument complement. And this is an actual picture of this unit. You see the tray is the blue metal background here that everything is mounted on. In the center top are the 2 central processing modules and the stints that data to and from it. On the top left, we have memory units 1 and 3. Top right, memory units 0 and 2. So 4 units total that we use 1 of at a time. And the same thing here with the CPMs and stints, we use 1 of those at a time. On the left side middle is the control unit science data formatter and remote interface unit side A. And on the right side is side B, which is what we were operating on at the time of the failure. And then there's a power control unit and a backup control unit in the center. So when we talk about side A of the CUSDF and side B, we're talking about these 2 boxes. Okay, when we get an anomaly like this in the telescope and it's something non-trivial, what we generally do is form what we call a tiger team, which is gathering together a bunch of experts, mostly engineers, but some scientists as well, and managers to figure out what's going on and what the path forward is to investigating the failure and trying to find a workaround for it. So I'm not going to read all of these names here, of course, to you, but I just want to show you that it's a lot of people. It takes a village really to analyze a failure like this on a telescope as complicated as Hubble. So on the left, you see a bunch of people in the current operations team, and then some independent members we brought in from outside, some from other parts of Goddard or NASA, others, people who used to be working at Hubble but had retired, but were brought back because they have knowledge of this particular system that we were looking at, and they kindly came back because everybody has an attachment to Hubble, has ever worked on it. So generally, if you call them, they will indeed show up. Okay, to go through the days in a little more detail. The first recovery attempt was on June 14th. All of the instruments had been in safe mode since the 13th. On the 14th, we tried a quick restart of the SSCDH, and we got 35 minutes of successful normal mode runtime before it failed in the same way that it had originally. So clearly we had a recurrent problem, even though temporarily we were able to effectively reboot it. So next step, as you may remember from Apollo 12 after the lightning hit, well, try SCX to aux, basically switch to some other components. And in this case, I'm using this to indicate switching individual components, which are pretty easy, like throwing a switch, to try out. So we did a bunch of the near-term recovery efforts over this between the 16th and 19th of June. On the 16th, we attempted to do a hardware dump and recover using memory module 3. We had been on 1, so this was basically trying to switch to unit 3. That was unsuccessful. On the 17th, we tried to load zeros, perform zero memory program, just load a bunch of zeros into the memory and do a dump to confirm that they were in there. We tried that on both memory modules 3 and 1. Both failed with the same signature that we saw the previous day. On the 19th, we upped our game a little bit, tried multiple cycles of doing trying to load the memory with zeros and dump the memory contents. And we did that on memory modules 1, 3, and 2, and all of them were unsuccessful. So that was beginning to look like, maybe it's not a problem with the memory, since none of the backup units were helping solve the problem. I apologize a little bit for the details here, but I am going to show you this chart recurrently because it helps to show you why it's hard to figure this out, but also, how we went about it. So before the anomaly, this diagram is basically showing you the components of the SSCDH. So before the anomaly, we were using stint and CPMB and CUSDFB. So we're configured on side B of the SSCDH. These components talk through the upper bus, although it's lower on the diagram. It's a little weird, but this line here is the upper bus, and that connects down to stint B and over here to CPMB and memory module 1. You can see from this that memory module 3 is also in that upper bus. So if you switch those two, you can see if it's the memory unit, but you don't test whether the bus has a problem. So if you use memory module 2 or 0, you'll actually test this lower bus, and you'll see we did that at one point. So anyways, everything's on side B right now using memory module 1 and the upper bus. So first thing we did, as I said earlier, is to try switching from memory module 1 to memory module 3, but keeping everything else the same. And that still kept us in the upper bus. No joy doing that. So then we tried switching to memory module 2, keeping everything else the same. That not only changed the memory module, but switched us to the lower bus and checked this wiring connection to make sure there was nothing wrong there. That also didn't fix anything. So this brings us to, we're at the end of this diagram here. Again, I'm not going to go through this in detail, but I wanted to, again, keep showing you the level of complexity involved in doing this. So starting on the 13th, we had the initial anomaly, did a couple of memory dumps, temporarily worked, formed the Tiger team on the 15th, tried switching to different memory modules here on the 16th, 17th. While this was happening on the spacecraft, we started working on the ground, the Vestas ground test facility, to see what would be involved if we wanted to change the memory modules in stint to their backups. We hadn't done that in a while, so there was it was prudent to test that on the ground. So we were doing that in parallel with all this other stuff on orbit in case we needed it. We had an ops briefing where the engineers came back and talked to project science and project management about what had been going on, and basically saying none of the troubleshooting of the memory provided any success. So at that point, we stood down, actually gave people a day off because they'd been working really long hours for this entire week and figured they needed to be refreshed a little bit. Then the Tiger team met, and recommended the next thing we should try was switching to the memory module A and stint A. So they made that recommendation on the 21st. So this basically was our last attempt to regain operations using side B of the SSCDH and of the spacecraft, which is the side we had been operating on since 2009. Tiger team recommended moving forward to try to use all of the available redundancy on side B first before going over to side A of the CUSTF. So that meant because they're cross-wired, we can stay on side B, but switch the CPM and the memory module and the power control unit to side A, and that would allow us to also do some tests to figure out if it was the interface module or the memory module causing the problem. We tested the procedure in the ground in that vehicle electrical simulation test facility, VEST, and we're confident that we could do it without harm to the spacecraft. And the plan was, if we were successful, recover the payload computer to normal mode, evaluate performance. If it looked good, proceed with instrument recoveries, return to normal operations. If the switch to the memory module A was unsuccessful, then the next thing to do was try to power cycle the 28-volt input to the CUSTF side B. We hadn't done that yet, even though power cycling fixes a lot of things on the Earth. You always run the risk of causing additional problems. So we try to, not do that prematurely, but once we tried all of these other things, there was no harm in trying this. So we power cycled that input, and that was unsuccessful as well. And this was basically the last available action we could take on side B before basically being forced to switch to side A of the command unit science data formatter. And because of the way that spacecraft is wired, that meant we had to switch to side A of the spacecraft as well, which is why it's a big deal. Because to do that, you got to basically shut off the brain of Hubble first, the HST 486 computer, and then hope you come back and regain consciousness, as it were, on the other side. So back to this diagram again. The thing we're switching is from stint B and CPM B of the NISKey to CPM A and stint A, leaving everything else in the original configuration in side B and with memory module 1, hoping that this backup component, the problem was in here somewhere, or in here, and switching here would take care of it. So we tried that. We also tried CPM A with memory module 2 on the opposite bus. Neither of those worked. There was no useful information out of trying to distinguish between failures of CPM B and stint B. We then switched, as I showed you, using stint and CPM A, did full power cycles on the SSCDH, on B and memory module 1, and then power cycle the entire tray, and then tried that recovery that I showed you to stint CPMA with memory module 2. All of these things were unsuccessful. So very frustrating time for us with all these possible solutions that made perfect sense that they might very well work, and then one after another did not. So the problem clearly lies somewhere outside of one of these components, but in the SSCDH somewhere. So just a brief word here for how we go about failure analysis. We use something called Fishbone Diagrams to keep track of what we're looking at. Again, don't be freaked out by looking at this. I'm not going to go through it in full detail, but partway through this process, about halfway through, this is what these Fishbone Diagrams look like. So basically, you list along here the different kind of failures that are possible, and then you try to assess whether they are or are not the cause of the problem, whether it's a possible cause, whether it's likely or not likely. You can see along the top here, we looked at intermittent failures of the first memory module, upper and lower bus failures, failures in the memory modules, or latent failures in memory modules. And you see here, not likely, possible but unlikely, possible but unlikely, not likely. So none of these things were coming through as something that was likely the cause of the issue. It's possible that the memory units on different data buses might be there, but didn't look terribly likely. Failure of the CPM alone didn't make any sense given what we were seeing. It was possible here that the power unit had some kind of issue, or the conversion of the 28-volt spacecraft power to the 5-volt power that goes to the SSCDH components. Maybe something in there was going wrong, a power input clock failure, something we couldn't rule out. And then possible but unlikely was a problem with the side B CU-SDF, which didn't seem likely because of the successes that we had. So there's possible identification here and here that we had to investigate further. And by the end of the investigation, this is what this diagram looked like. So it got way more complicated. Basically, anything that's green over here has been eliminated as a possible cause of the problem. If it's in orange, it is seen as a possible cause. And if it's in red, it seems very probable that the cause is somewhere on that track. I won't go through the detail here, except to say that in the end, it was, we really think the problem is in the power converter. And this is the device that takes the 28-volt spacecraft power and converts it to both 5 volts and 12 volts for use in the SSCDH. And the original SSCDH used both. The new one just uses 5 volts. So something in that converter is likely causing the issue and causing the problems elsewhere. So trying the simple try SCX to aux, switching some components off and on didn't work. So then we had to try, as Spock would have said, cross-circuiting to B, which, except in this case, really is cross-circuiting to A, because we started out on B. As far as I know, in Trek, they never actually went the other way. They always started on A. But we're going to try to switch sides from side B to side A and effectively take Spock's advice on that. So after the on-orbit testing and the Tiger team analysis and the testing on the ground, we're going to switch to CU-SDF-A and regulator A. So again, this becomes more and more prevalent. Regulator A is what changes the voltage level, a step down voltage from 28 to 5. And that more and more was looking like the cause of the problem. So switching to regulator A, in theory, if that was the problem, could fix it. You have to switch those two devices together, as well as the data interface units and data management units. They're not cross-strapped to the opposite sides. So we switch to CU-SDF-A. You have to do the more extensive side switch on the telescope, not just inside the SSCDH. So in terms of what we do switch, the DIU, data interface unit, data management unit, a number of the modules inside there all need to be switched. Sorry, my keyboard is super sensitive today and bouncing slides when I don't want to. You have to update the software in the 46 computer, and switching these modules in requires actually stopping this main spacecraft computer, the 46, like I mentioned earlier, and makes us switch down to what's called the Pointing Safe Mode Electronics Assembly, the PSEA, which is a backup system that's designed for just the situation when the main computer is not available or goes out. You have this very limited capability PSEA to control the spacecraft and keep it power positive and warm. So that's part why the side switch is scary. You don't like going down into PSEA mode if you don't have to, but that's what it's there for. Within the SSCDH, the stint, processor module, oscillator, power bus are all switched. In this case, that's consistent with what we've previously tested on the ground. We've also have command procedures and process this is defined for science instrument transitions. The RIU, remote interface unit, can actually stay on side A where it was. I can talk to either side A or side B of these other components, so there's no need to actually switch that. Again, showing you how complicated it is. There will not be a test on this, but this is the agenda for the review session we had of the planned side switch to make sure that it was A, going to work, and B, was going to be safe for the telescope to go ahead and do this. So you can see 11 major sections of this, and actually this is the same process we use for any major activity on the telescope. But again, I hope this helps convey to you why it takes so long sometimes to address and find a way to fix telescopes safely. Again, also just showing you the engineering team that's working on the side switch, people from flight software, on the spacecraft computer, on the payload computer, ground test folks, data management system, optical telescope assembly, pointing control, et cetera, on and on and on. You had people from all of these different disciplines inside the HST project had to be working together to make sure everything went smoothly and we didn't hurt anything in the process of making this change. Okay, so here's our friendly diagram again. You'll see the main switch is off of CUSDF B, Stint B, CPMB over to side A. We switched to memory module 2, which is the default for side A instead of memory module 1. And on over, we didn't show before, data management A. We had been using data management system B. We switched to A as part of the overall spacecraft side switch. This was the timeline for the switch. Again, I'm not going to go through this in detail. Over here, the first half of the diagram shows you when we were under control of the PSEA. And then midway through, we switched back to the 486 computer, the spacecraft computer, after it came back up. So about half of the procedure was done under PSEA control and half under the regular computer. And then spanning that was the reconfiguration of the payload. And you see where science restoration comes in about 2/3, 3/4 of the way through this process. And then you recover the science instruments one by one. Each one takes multiple hours to do. Okay, the initial conditions for the side switch. Vehicle was in normal data management unit, normal mode. The PSEA can be configured to either use the main 3 gyros or backup gyros. They're very low fidelity in comparison to mechanical gyros. In this case, the normal gyros were actually working, so we use that and maintain better pointing control. The SSCDH is in fixed mode, which is where we're stuck basically. And we were on side B for all of these components here. Science instruments were in safe mode. So the process would be to command hardware sunpoint, reconfigure the data management modules to side A, reconfigure the data interface unit to side A, recover to HST 486 control, and get out of PSEA control and back to the main spacecraft computer, and reconfigure the SSCDH to the A side, which meant switching the CUSDF, the stint, and the memory module, or the central processor module to side A. Later on, we would recover the wide field camera in real time using ground commands as we entered onto the science mission schedule. And the other instruments, the Advanced Camera for Surveys, the Space Telescope Imaging Spectrograph, and the Cosmic Origin Spectrograph were recovered from safe mode via the return to science SMS autonomously in the pre-planned commanding. We didn't have to do that from by ground command as we did with F3. Okay, some on-orbit history here for the SSCDH. As I mentioned earlier, Hubble was operated on side A until October 15th, 2008, when it was switched to side B because of a failure on side A. The second SSCDH was installed during the last servicing mission 4 in May of 2009, and has been exclusively operated on the B side until now. We did do extensive ground testing on side A before launch of SM4, but it had never been used in orbit. Okay, again, more detail than you want, but if you're interested, you can read through. This shows you all of the components that were switched, that had to be switched from side B to side A. So data interface unit, communications, timing, telemetry format control, prime receiver. And that actually was useful. We were on receiver 2, and that had lost one of its transponders, and we could no longer do ranging using it. We had to rely on other agency assets to figure out the Hubble orbit. MA receiver 1 still is fully operational, so we should be able to resume ranging using Hubble assets to help refine and update the orbit of Hubble. So that's one positive outcome of all of this. Data interface units was switched, data interface units, and the 486 mask from B to A. Inside the SSCDH itself, we talked about all these components switching over from side B to side A. And the thing to appreciate here is doing the switch thus means you're not just hoping that the failed component inside the SSCDH works on its side A, you're hoping that all of these other components also work after having sat unused for 11 years in orbit since the last servicing mission. So that's the thing that probably made us more nervous than anything else, is that all of these backup sides had to function. And there's no reason to think they wouldn't, except that you use something for 11 years, who knows. So that's where we crossed our fingers. SIs could stay on their current sides because they're cross-strapped to use either side of the spacecraft. We monitored all of the subsystem status throughout the entire transition until we got back to a science mission schedule, evaluated their performance, looking at calibration curves and limits, and found normal science mission schedule execution of both the payload and spacecraft. The computers executed fine. We were able to record and play back science data and memory and science data dump with the CUSDFA. All were verified to work properly. And then we did a full checkout of the science instruments using the science mission schedule. And we'd monitor, of course, in real time when we had direct communication. So on Saturday, July 17th, we actually were able to restart science observations. And I show you here 2 of the first images taken. These were kindly given to us, or PI of this program, Julia Del Canton at the University of Wisconsin, released the proprietary hold on these data to allow us to show the community and the public that things were working again. So it's a galaxy here with a very unusual extended spiral arms that go way out from the galaxy. And then another separate picture looking at a pair of colliding galaxies. We also very early on looked at a globular star cluster and aurora on a giant planet Jupiter. So as you can see, things right off the bat, as soon as we got back up into side A, went back to a normal mode of operation. Just want to again say a few words about the recovery team. We did, as I mentioned, get some Hubble alumni to come back and help, basically giving us decades of mission expertise that could be brought to bear on the problem, particularly retired staff to help build the telescope, and in specific, the Science Instrument Command and Data Handler, where the payload computer resides, were critical for helping us figure out what was going on. Other people dove into Hubble's original paperwork, going back 30, 40 years to understand what was going on and how the SSCDH was built and how best to fix it. So one of the benefits you get for a program that's been going on for 3 decades is this incredible base of experience and expertise. As our anomaly response manager at Hubble noted there, this engineering team worked with scientists like myself and managers at both Goddard and the Space Telescope Science Institute that run science operations for Hubble over a period of more than a month to diagnose and safely return Hubble to science operations. And here you just see a couple of snapshots inside the Hubble Science Operations Center during the restoration work on July 15th, where they were actually commanding the side switch in recovery. So in summary, Hubble has returned to normal science operations using side A of the spacecraft and SSCDH, and we have the same quality of observation and efficiency as prior to the anomaly. Demand for observing time on the telescope continues at historically high levels. After more than 31 years, we still have large oversubscriptions in terms of requested observing time versus available time in a calendar year. Science productivity continues at the pre-anomaly levels, and we're looking forward to operating in parallel with the James Webb Space Telescope after it launches later this year. The most recent data in its launch is now December 18th. They're basically waiting for the Ariane rocket launches to catch up. We're behind on some previous launches. So this delay from October to December was actually because of Ariane launch system delays, not because of anything happening with Webb. We would like for Webb to get up there, and we look forward to providing complementary coverage of shorter wavelengths that Hubble sees, the ultraviolet and the blue end of the optical, which the JWST does not see. It sees the red part of the optical and out into the infrared. So having both observatories operating at the same time gives you much better color and wavelength coverage. We are, now that we're back to operations and have a little more time on our hands, looking at ways to recover partial or full use of side B if it's ever needed in the future. So we've switched to side B to side A to get full operations back. But if something happens on side A in the future, we might need to see if there's any way we can go back to side B and get some kind of operations out of it, even if not the normal mode operations that we're doing now. There are some thoughts that if we cool down and power off side B completely to get rid of transient charges, capacitors, whatever, that maybe that might help. Or we might be able to find a way to work around the payload computer if that turns out to be a permanent failure, that the power cycling and cooling doesn't help. That would probably support more limited operations than we do nowadays, but it might allow us to continue operating rather than shut down. So the engineers are off busy looking at those possibilities. That's going to take a lot of investigation and a lot of planning. So we hope there's no need for that for quite some time. But it's nice to know that there might be further options if needed down the road. And just to acknowledge here that Hubble's engineering team is beyond compare, and sometimes pull rabbits out of their hats with great efficiency and effectiveness. And that allows us to say we still hope to continue to operate Hubble into the next decade and perhaps beyond. And if you would like more information on any of this, go to our main website at nasa.gov/Hubble. And you can find stories on all of this, as well as ongoing science results and image and other data releases. So thank you very much for your attention, and hope to see you at Fort Collins Comic-Con in person next year. Thank you.